In today's lecture, we will learn about randomized linear time minimal spanning tree algorithm. Okay, so, the standard deterministic algorithm for solving the minimal spanning tree are, say, the Prim's algorithm, and then there is Kruskal's algorithm, and the third algorithm is the Boruvka's algorithm. These are the standard deterministic algorithm. So, Prim's algorithm, if you remember, it is about taking an initial spanning tree and then growing it. So, that if you do the correct implementation, the algorithm can run in m plus n log n time, okay, whereas Kruskal will run in order of m log n, and Boruvka would also run in O of m log n. So, this algorithm basically grows an initial spanning tree. So, let us say you have the part of the spanning tree to start with, and then that defines a certain cut. You add the least weighted cut edge, keep on doing it repeatedly, you will get Prim's algorithm. Whereas Kruskal's algorithm, you have an initial forest, you sort all the edges and you keep on adding the edges one after another, under the condition that the added edges do not introduce a cycle. Okay, so, this basically sorts the edges and keep adding edges without cycle formation. Boruvka's algorithm, on the other hand, is, you can think of it as a parallel algorithm. At every vertex, add the least weighted edge at every vertex, and then you, let us say, cluster it, or you can contract the graph and repeat. So, when you consider the least weighted edge at any particular vertex, so let us say if you are looking at this particular vertex, there might be lot of edges out of it, and the least weighted edge. This can be done for every vertex, because if you imagine this vertex as a single element and everything else in the remainder of the graph. So, if you think of the cut that is obtained by considering this vertex, by considering just this single vertex, this edge becomes the least weighted edge out of that vertex, becomes the least weighted cut edge, which by cut property will surely belong to every minimal spanning tree, assuming that the graph has distinct weights on all the edges. And this could be done for all the edges simultaneously. It could happen that the least weighted edge is shared between two vertex. For example, this UV edge could be the least weighted edge for U as well as for V. In that case, you will get only one edge instead of one edge for every vertex. You will get, in the worst case, one edge for every two vertex. So, you will get at least n by 2 edges when you do this in one. So, let us call that as the Boruvka phase. So, in each Boruvka phase, at least n over 2 edges are added to the MST. Okay. So, you can keep on doing this till, so once you add these edges, two vertices which share an edge is being contracted, you get a super vertex, and then keep on repeating this for the new vertices formed. So, if you had let us say 5 vertices, 5 edges out of this, and you had let us say 4 vertices out of this, when you contract them, this edge is common, that is gone, and then there are 1, 2, 3, 4, 5, 6, 7 edges out of the blob that is formed by, or the super node that is formed by combining these 2 vertices. Okay. So, that is a Boruvka phase. Okay. Why are we looking at it? Well, Boruvka's algorithm will become a crucial ingredient of the randomized linear time minimal spanning tree algorithm. Okay. So, I will first describe the algorithm, and then we will look at why this algorithm runs in expected linear time. Okay. So, let us call this as randomized MST. Okay. So, input will be a weighted graph and the output will be the MST. It could even be a weighted forest, in which case we will get a minimal spanning forest. So, output will be a, we will think of it as a singly connected graph. So, the output is a minimal spanning tree of G. Okay. So, the first step is we will take this input graph and run the Boruvka algorithm on it 3 times. So, we will write it as run 3 phases of the Boruvka algorithm. Okay, let us add some commentary to this step. Note that you can implement each Boruvka phase in linear time. Okay, so, 3 phases would essentially mean again linear time. So, can be implemented in O m plus n. Okay, m here is the number of edges and n is the number of vertices. Okay. After 3 Boruvka phases are run, okay, each phase means you look at all the vertices simultaneously, and for each of them you add the nearest neighbor, and then you contract them. So, that contraction is also included in a phase. So, that entire thing can be executed in let us say linear time. Okay. Now, after this has been done, number of vertices remaining is at most n over 2. Okay. So, why did we run this Boruvka phase? Well, one thing is we could get a saving in the number of vertices, but the edges could still be large. So, what we do is we will throw away some of the edges. Okay. So, this is the only place where randomization really comes in into this algorithm. So, we will randomly select the edges of this reduced graph. So, we can think of it as you toss a coin and the bias, let us say it is p, we will choose p to be equal to half. So, randomly select each edge with probability half. So, you toss a coin with bias half, the coin results in a head, then you include that edge, otherwise you throw away it. So, we will get a graph, and that graph we will call that as the graph obtained as let us say G1. Our original graph was G. After we have shrunk, we will get some particular graph, let us call that as G prime, or we will call this as G1, and here whatever graph we get, we will call it as G2. Now, note that G2 can have at most n by 2 vertices, but the number of edges is also reduced, because the expected number of edges will now be half of the number of edges in G1. So, if G1 contained at most m edges, then we can say number of edges is less than, so here when I say this is in the expected sense, so expectation is less than n by 2, and number of vertices is also less than, let us say, n by 2. So, first step was to run 3 phases of Baruka. There we would have got a forest, we will call that as, let us say, C is the edges of the MSF. Okay. The edges that we will gather towards making our minimal spanning tree in the Boruvka phase, those we will call as C. Okay. And now we have a reduced graph, which we were calling it as G2. Okay. Now G2 is a subgraph of the contracted graph. We will try and construct the minimal spanning forest for G2. G2 may not be connected, G2 could be connected, but whatever it is, we will just run the MST algo for, or let us say on G2. Okay. So, now the MST algorithm, it is basically giving a minimal spanning forest. So, we should have been a little more careful and said that this is a weighted graph. It need not be connected and the output is a minimal spanning forest. If G was a connected graph, then the output would have been a minimal spanning tree. Okay. So, we will run the MST algorithm on G2, we will get a forest. Okay. So, let F be the forest obtained. Now, this F is a random quantity, in the sense depending on the choices that we make in step 2, we could get different forests. In the second step, we were selecting a subgraph of the original graph, and for that subgraph there is a corresponding unique forest. We can say unique because we will assume that the weighted graph that is initially given to us contains distinct weights on every edge, and therefore, any subgraph will also have that property, and therefore, when we run the minimal spanning tree algorithm, that is this same algorithm, when we run it recursively, the forest that we obtain will be unique forest, but this is unique only for the random choices that we have made. If we fix the random choices that we have made, then for each such fixed choice we will get a unique forest. Now, that forest therefore is a random quantity. Now, once this forest has been fixed, what we will do is there are certain edges that we can throw away. Looking at the algorithm, let us ponder why this algorithm might be a good algorithm. Okay. When does it not give linear time algorithm? That might be because there are a large number of edges, but here we are running the algorithm on reduced number of edges. We run the minimal spanning tree on a smaller graph. Okay. So, it might be possible to do it in less time, but after running, why is this useful? After we have got this particular forest, what we can do is we can throw out certain edges. Okay. These are those edges whose addition will create a cycle in the forest, and those edges in the cycle that we are considering, those edges are going to be the heaviest edges. So, we will call these things as the heavy edges. We will later on define more properly what are heavy edges. So, right now I will just write down the algorithm. So, throughout the heavy edges, what are heavy edges? We will later on provide a definition based on F. Okay. So, we will call this as the F heavy edges. The key thing is these F heavy edges will not be present in any minimal spanning tree. Okay. So, it is safe to throw that out. So, it does not depend on our choice of F edges that can be safely thrown out. Okay. The choice of which are the heavy edges might depend upon the particular forest that we had picked, but once we have identified that a particular edge is heavy for some particular forest, that is a edge that surely is not going to be present in the minimal spanning tree. This we will see a proof of it later. And once we have thrown out the F heavy edges, the remaining edges are called as F light edges. Okay. So, these edges are being thrown out from G, from the original say graph G1. So, now once the heavy edges have thrown out, we can compute the MST for okay. So, these we will call as the light edges. Okay. So, you compute the minimal spanning tree for the light edges and then return. So, light edges, if you call it as let us say L, we will return L union C, that is the edges that we initially picked as the minimal spanning forest. Okay, will this always return a correct answer? Well, these edges C had to be present in all minimal spanning trees. Further, this is the contracted graph, and from the contracted graph the edges that we have thrown out are the heavy edges, and we will see that heavy edges deserve to be thrown out. Okay. So, on the remaining graph, if you compute the minimal spanning tree, though the new edges that you will obtain are L, all of them need to be present, and therefore, if you return L union C, that will be a minimal spanning tree of G. We need to figure out what exactly are these heavy edges. Once we figure out heavy edges deserve to be thrown out, we need to analyze this algorithm and see what is the overall running time. So, let me first provide you with the definition of F heavy edges. Okay. So, F heavy edge means it is with respect to the particular forest F. So, F is a forest, okay, and let us say our initial graph was G, and F is a forest for G. Okay, it need not be a minimal forest, minimal spanning forest, just some collection of edges. Okay. Now, if you have a forest, okay, so let me say that the forest edges will be colored in black, and the non-forest edges, let us say they are colored using a different color. Okay. So, now if you take any arbitrary pair of vertices u and v, okay, between these two vertices here in this example, there is no path consisting of just the forest edges, because they belong to different connected components. But suppose they are in a connected component. So, let us say this was your vertices, and if you look at V and W, in the forest there is a unique path from V to W. Okay, unique in the sense you do not trace the same edge twice. If you allow only one transition through each edge, then there is a unique path from U to V. In fact, for any, if you take any tree and if you take a pair of vertices, there is a unique path from one vertex to another. Okay. Since we are looking at a weighted edge, we can look at this unique path and look at the weights that are there on this path. There could be a direct path between V and W. So, let us say this is some path from V to W, and probably all, I mean, when these things have given weight, and this is your U and this is your W. There could have been a direct path as well. Now, let us compare the weight of the direct path to the weight of the individual edges in the path. Okay, we will call an edge F heavy. So, an edge UW is called F heavy if 1 U comma V should be in the same component, connected component. 2, the edges on the unique path from u to v must all be of weight at most weight uv or uw. Okay. So, if you look at this path, if its weight is 10, if everything here is of weight less than or equal to 10, then this is called as a F heavy edge. Okay. So, if this edge is of 10, okay, if these were the weights, then this is not an F heavy edge, because every weight is at most 10. So, how do we determine if a particular edge is a F heavy edge? So, let us look at the unique path from u to w, that is, if there is such a path, and so let w f u v or u w denote the weight of the heaviest edge in u to w path. If the weight of u w is greater than w f u w, then u v is called an F heavy edge. Okay. So, you look at the weight of u w, every other edge on the path is of weight strictly less than the weight of u w. Okay. So, if these were all weights, say 9, 7, 6, 5, 2, 1, 3, then all these weights on the u w path are strictly less than the weight of u w, okay. And therefore, u w will be called as an F heavy edge, that is, if all these edges, I mean if this was the unique path, these are all edges in the path, in that case u w would be called as an F heavy edge. If this was 10, then this is not a F heavy edge. Okay. So, the edges which are not F heavy, so not F heavy is by definition F light. Okay. And the important fact for us is F heavy edges are not present in any MST. Okay, that should be clear, because that is just an application of cycle property. So, cycle property says that the maximum weighted edge in a cycle will be absent from all minimal spanning tree. Okay. So, if you take the maximum weighted edge, since we are looking at graphs where all the edge weights are unique, if you look at the maximum weighted edge, all the other edges are of strictly less weight. So, if you, so let us say there is a cycle, and if you look at the maximum weighted edge in the cycle, that edge can be thrown out from all minimal spanning trees, that is what the cycle property says. So, here when you have a path between u and w, and every edge on that path is of weight strictly less than the u w weight, if you add this u w into this particular path, you will get a cycle, and this becomes the heaviest edge of the cycle. So, that edge deserves to be thrown out from minimal spanning tree. Okay. So, F heavy means it can surely be eliminated. Okay. Now, let us just revisit the algorithm. The algorithm says you randomly choose a subgraph of G1, where G1 is a graph obtained after running 3 phases of Boruvka. From that randomly chosen subgraph, you construct its forest, which is going to be a random forest for G1. Based on that random forest, throw out all the heavy edges. those heavy edges we know are not going to be present in any minimal spanning tree. We need to determine these heavy edges, means we need to, when given a particular graph f, we need to classify the edges as heavy edges and light edges. Okay. This can be done in linear time. So, this is based on something known as MST verification algorithm. We will not go into details of those algorithms, but we will just assume that the f heavy edges and the f light edges can be segregated, and this can be done in linear time. The algorithm is by Kargar et al. Okay, so Kargar had given this randomized algorithm, and the analysis was done by Tarjan et al. Okay, so the algorithm given by Kargar was shown to work in randomized linear time. So, that algorithm basically verifies that certain edges are heavy edges and the other edges are light edges for any arbitrary tree f. Okay. So, now we said that the heavy edges can be thrown out, okay, but how do we analyze the total time? Where did we get these savings? Okay. So, how many heavy edges would be thrown out? The utility of this algorithm is significant only if large number of heavy edges are thrown out. We have two recursive invocations of the MST algorithm. Here, where the MST algorithm is running on an input of size roughly m by 2, because the original graph, even after running multiple phases of Boruvka, after running 3 phases of Boruvka, might have, let us say, m over 2, could have a significant fraction of the initial edges. Okay. The expected number of edges could be m over 2, and later on we have another invocation of MST where all the heavy edges are removed. What we will argue is the heavy edges are large in number, or in other words, we will show that the light edges for any f that is randomly chosen will show that the light edges are not too many. Too many for us here means, let us say, O of n. Okay. There are a linear number of edges in the size of the graph. So, let us look at this sampling a little more carefully to count the number of f light edges. So, this is the question that we will answer: how many light, so f light edges will be present. So, what we want is the expected behavior or the expectation of the number of light edges. Okay, so, what does this algorithm really do? So, let us say we had this contracted graph which we will call as, let us say, G for the time being. So, this, let us say this was the graph obtained after contraction. What we do is on each edge toss a coin. Okay. So, maybe this will be included, this will be included. Okay, the marked edges, okay, maybe they will be included after a coin toss. So, based on the result of a coin toss from the graph G, okay, we had obtained the graph. Let me just color it in red. This is a subgraph of the original graph which we will call as H, and for H we will obtain, so H is this smaller graph. For H we will have to obtain a spanning forest, which would be, let us say, I have not put the weights, but suppose it is something like this. Okay. So, that is the way the algorithm progresses. from G, this is the contracted graph, we will sample and we will go to H, and from H we will go to F. Okay. So, F is the minimal spanning forest. Now, based on F, obtain, let us say G prime. G prime is a subgraph of G, and we are interested in how many edges are really present in G prime. Okay. What we will like to say is that in an expected sense, large number of edges will be thrown out of G based on this F. Let us look at the edges in G. We will write it in the increasing order of their weights. In the algorithm, we do not sort the edges because that is too costly to do, because if you sort all the edges, your algorithm's running time will be m log m, okay, which is more than linear time. So, we will not sort, but let us imagine the vertices in the sorted order. Okay. So, we want to figure out which are the edges that would remain in G prime. Okay. So, after that contraction phase and after throwing out certain edges based the intermediary minimal spanning forest, what are the edges that would remain? Okay. How many such edges would be there? Look at the edges in the original graph, let us call it as E1, E2, Em. Okay. So, this M is not the total number of edges in the input graph, but it is the number of edges in the contracted graph. Okay. So, let us say it was E1, E2, Em. What we had done is we toss a coin. Okay. So, let me just say that I will denote the output of the coin toss. Okay. So, heads, and some of them will be tail, tail, head. Okay. The heads are the ones that I would pick to obtain the graph H. Okay. And then based on H, some of the edges in H. Okay. So, look at all these edges in H, few of them, okay, I will add to the forest. Okay. Once the graph H is fixed, it has a unique minimal spanning forest. Which are the edges of the forest we will need to worry about. Once the edges of the forest gets fixed, the edges which will be removed also gets fixed. Okay. So, from F we will basically compute G prime. Okay. So, the entire process we can view as we have all these edges E1, E2, Em, and we toss the coin, and after the result of the coin toss is obtained, we could take decisions. So, now let me just look at the ith edge in the sorted order. Okay. Will this edge be present in G prime? Okay. Before that, will this edge be present in F? Okay. So, the question of whether this will be present in F. So, does Ei occur in F? Well, it depends on two things. One, the outcome of the toss. If the toss had resulted in a tail, then certainly it is not going to be included in H, which is not present in H is going to be included in the forest. But even if this edge was present in H, if the weight of that edge was too much, or if it was not a suitable edge for the minimal spanning forest, it would have been thrown out. Okay. So, I will write that as the MST criterion. So, only if this particular edge Ei satisfies the outcome of the toss requirement and the MST criterion will it be present in the forest. Now, the outcome of the toss is not dependent on anything else. These are independent coin tosses. So, it just depends on that particular toss. The MST criterion does not depend on any edges after Ei. If you look at the sorted order, the only edges which plays a role in the MST criterion are the edges which appear before ei. There are many edges in the graph G which had gotten added to the subgraph H. Amongst these, look at those edges whose weights are less than ei. Those alone would determine whether ei is present or not. So, look at the subgraph of H formed by restricting the attention to edges which have weights which is strictly less than ei. Now, if you look at the edge ei, so let us say ei is u comma v, if u and v are in the same connected component in this subgraph, okay, which is a subgraph that we are looking at. Look at H, H is a particular graph which is a subgraph of G, and inside H restrict your attention to only those edges whose weights are less than ei. They would have formed a subgraph amongst themselves. Now, if u and v are connected in that subgraph, if you add the edge connecting u and v, they will form a cycle whose weight, whose largest edge is going to be uv, and that's why uv is not going to be present. Okay. So, this edge occurs in F. In that subgraph, if you add u and v, they do not form a cycle. In other words, u and v belong to different components in that subgraph. Okay. So, if they belong to different components, ei will be present. If they do not belong to different components, ei will not be present. So, this decision is entirely based on the outcome of the coin tosses E1 to ei. The result of the coin tosses starting from E1 to ei determines the subgraph, and once the subgraph is determined, the decision of whether ei is to be present in F or not is completely made, and therefore, the other edges do not play any significant role in whether ei occurs in F or not. Okay. Now, what we are interested in is the light edges. How many light edges are there? So, in order to analyze that, we will do a small trick. What we will do is the following. Let us see here, we constructed the subgraph H, okay, and then after H is ready, we were looking at the forest, and then we were looking at the subgraph of G by removing the F heavy edges. We will look at it in this increasing order of their weights itself. When an edge is being considered, that edge, if it is included into H, it might create a cycle in the already existing edge. Okay. So, consider creating H iteratively. Okay. So, which means start with empty set, keep on adding edges to H on the basis of the coin toss. Okay. These edges considered in increasing order. Okay. So, we can imagine that the coin tosses have already been done for all the edges, and we are just now taking those coin tosses and deciding which are the edges of H. While we do this, we can also construct the spanning tree F side by side. Okay. Now, when we add an edge to H, we can at that point wonder whether that edge will create a cycle in H. If it creates a cycle in H, that is not going to be an edge for F. In fact, that is going to be an F heavy edge. Okay, once again, while we are looking at construction of H in an iterative fashion, whenever we are adding a particular edge to H, that is, if the coin toss resulted in a head, we could have added that edge, but at that stage we will check whether that edge creates a cycle in the already constructed spanning forest. Okay. So, we had, let us say, some particular set H, and along with it we had a spanning forest, a partial spanning tree, and while we are adding an edge, we look at whether adding that edge creates a cycle in F. If it creates a cycle in F, that edge is going to be a heavy edge. Okay. So, we will just mark out, so we will just ignore the heavy edges and we will just mark out the other edges. The other edges are essentially the light edges. Okay. So, each edge, I mean if you are looking at in this order E1, E2, EM, certain edges I will just mark out. This essentially means while considering E2, if I look at the iterative spanning forest, in that forest if I were to add E2, E2 would have been a light edge. That means adding E2 will not create a cycle in the spanning forest. Now, these light edges, I mean whatever I mark as light edges need not be present in F, they would be present only if the coin toss was successful. While we are constructing H, we said toss the coin, keep on adding to H. Okay. So, but we will just mark out an edge. So, we could just reverse the order in which these things is being done. In the sense, we will first check the edge. If the edge can be added successfully without creating a cycle in F, we will mark it out. And after marking it out, we toss a coin. If the toss results in a head, we will add that to the set H, and that edge surely would be there in F as well. Okay. But note that the starred edges are precisely the light edges. Okay. Now, note that this entire thing is the analysis. We are not trying to compute which are the light edges. You can think of it as an alternate definition of the light edges. That is, if you consider the entire construction of H in an iterative sense, that is in the increasing order of the weights, those edges which could have been added if the coin toss is successful without creating a cycle in F, those are precisely the light edges. So, if we want to count the number of light edges, they are precisely the number of starred edges. Amongst these starred edges, later on some of them would get added to F and the rest would stay there as light edges. Okay. So, we will summarize this by saying number of light edges is equal to number of stars. Okay. So, how do we estimate light edges? Well, you just need to count how many stars would be there. Okay. When does a particular edge get a star? Well, first of all the preceding edges should have, I mean if you look at the spanning forest by the previously selected edges, in that the vertices connecting E2 or EI, say UV, they should be in distinct components. Okay, we can think of this in a different way. So, the other edges which are not starred does not play any role, because we just need to consider the starred edges. So, we can think of there are all these starred edges coming up, and for each of them you toss a coin. If the toss results in a head, you include that into the spanning forest. Okay. They anyway gets added into H, and by virtue of it being a light edge, it also gets added in the spanning forest. Okay. So, we have this sequence of stars. Now, once all the edges have been exhausted, all the stars would also have been exhausted, but let us say we keep on tossing further dummy coins, okay, which does not really depend on any edge. Okay. So, these are the edges and these are dummy tosses. Okay. And we will keep on tossing till we get, let us say, n minus 1 heads. Okay. So, this is I mean in order to count the expected number of light edges, we are counting it in a slightly different way. So, there were stars on lot of edges. These stars gets decided based on the ordering. If we had a particular ordering E1, E2, Em, and if you had a particular outcome for the coin tosses, heads, tails, once this is fixed, the stars on the edges gets fixed. Certain edges would be starred edges and the others would be non-starred edges. The non-starred edges can all be thrown out because they are all heavy edges. So, now let us just look at the starred edges. Okay, there will be certain number of them, and we append those with certain, let us say an infinite number of dummy tosses or dummy edges. Some of these starred edges before the dummy edges would get added into F. At most n minus 1 of them gets added to F, because F is a spanning forest, it can have no more than n minus 1 edges in it. Okay. So, if we look at the sequence of stars and say we keep on tossing till we get n minus 1 heads, that would be certainly more than the total number of stars. So, let us say x is a random variable denoting number of tosses required for n minus 1 stars. Okay. So, if we do it on this particular sequence, by the time we get n minus 1 stars, we would have surely added all the edges to F. These coin tosses, if it had resulted in a particular F, all those edges would have been added. So, in particular, all the light edges would have been accounted. So, the random variable x, we can say it is greater than the number of F light edges. Okay. And since both these are positive, we can say that the expected value of x is going to be greater than the expected number of light edges. Okay. So, if we calculate this, that is certainly an upper bound on the number of light edges, okay. But x is just tossing coins till you get n minus 1 stars. But if each coin was of let us say bias p, the number of times you have to toss to get 1 heads is 1 by p. So, this will be at most. So, the expectation. So, expectation of x is nothing but n by p, where p is the bias of the coin, or n minus 1 by p. Okay. So, what this means is, in our algorithm, after throwing out these heavy edges, we are left with precisely n minus 1 by p light edges, where n is the number of edges in the graph that you are looking at. Okay. So, now we can just put in all these inductive steps and compute what is the total running time. P for us is 0.5. So, let us look at the total running time. So, if you denote it by Tmn, this is the total running time for a graph with, if the input graph contained m vertices, m edges and n vertices, then this is Tmn is going to be less than or equal to 3 phases, that is, let us say c times m plus n. So, we know that 3 phases, each of those phases takes linear amount of time. So, c times m plus n plus random selection, that is again linear time. So, that is absorbed into this. So, the first step is taken care of, second step is taken care of, last step just returns the spanning tree. So, those 3 together takes c m plus n. Now, if you run the MST algorithm on G2, okay, G2 will take T of m. The expected number of edges in G2 is going to be m by 2, and the expected number of vertices is n by Okay, so we had run 3 phases, so the number of vertices would be n by 8. Okay, each phase it gets divided by 2, plus if we had thrown out all the heavy edges, then G1 will contain T of the number of edges that is remaining will be proportional to, so it is n minus 1, n minus 1 here being n by, let us say we will bound this by n by p, okay, where n is only n by 8. So, n by 8 divided by half, so 2n by 8, and number of vertices is n by 8. Okay, so, this is equal to C m plus n plus T m by 2 n by 8 plus T n by 4 n by 8. Okay, so, that is a recurrence. So, T m n is going to be less than or equal to this quantity. If you plug in T m n is equal to, let us say 2 C m plus n, okay, suppose this is the bound that we impose, and then we will get, when it satisfies this equation 1, so T m n is going to be less than or equal to C m plus n. T m by 2 n by 8 is at most 2 C m by 2 plus n by 8 plus 2 C n by 4 plus n by 8. Okay, so, this is equal to C m plus n plus C m plus 2, so C n by 4 plus C n by 2 plus C n by 4. Okay, n by 4, n by 4, n by 2, and this is n by 2. So, this together is C n. Okay, so, C m plus, so this is C 2 C m plus n. So, we know that if we have T m n to be at most 2 C m plus n, then it satisfies the recurrence. So, this takes no more than linear amount of time in an expected sense. That is the randomized linear time algorithm for computing minimal spanning tree. Okay, thank you.